Okay, so everybody, it's going to start recording right now. Okay, so here's Sergei Treil with matrix weights and finite rank perturbations.
Okay, so let me start with finite rank perturbation. So we start with the self-adjoint operator in a Hilbert space, and we assume for simplicity that it is bounded. It can be unbounded, but kind of avoid unnecessary technical details. Just let us assume it is bounded. And let us consider standard kind of family of finite rank perturbation. So we consider operator V, which is kind of an injective operator from some d-dimensional space to the H. So it's where our perturbation happens, and it's parameterized by all possible self-adjoint Hermitian matrices gamma. And for the case when D is equal 1, so for this rank 1 perturbation case, it's just familiar setup with rank 1 perturbation, where gamma is here. The gamma here is real parameter, and without loss of generality, we can assume that a range of B is cyclic subspace, because from the point of, if it is not, then the operator B is just a sum of two parts. Closure of the object and the orthogonal complement. And on the orthogonal complement, nothing happens. The operator remains the same. So it's we just don't want to study what's not happened. Now let's do kind of the object. What are matrix valued measures? Matrix valued measure, you can think about this there are several ways of thinking about it. One is that it is just countably additive function defined on Borel subsets of the real line whose values are D by D matrices. And you can define as well operator valued measures as well, and kind of elementary point of view on matrix valued measure, it's just a matrix, each entry of which is a measure. And diagonal entries should be just honest to God, positive, non-negative measures. And off-diagonal entries can be complex valued measures. And we assume that for every Borel set X, the matrix is positive semi-definite, so it's Hermitian matrix. And of course, it implies. Now, what is kind of very nice about matrix valued measure? We can define trace, which is just the sum of diagonal entries. And we can see that all of diagonal entries are absolutely continuous with respect to this trace. And so measure is absolutely continuous with respect, this matrix measure is absolutely continuous with respect to this scalar measure mu. Now, why the absolutely continuous function is important? Because if you consider general operator valued measures, there are no problems integrating scalar functions against this measure. It's nothing new. But if you try to integrate vector valued function, for example, something like to compute weighted L2 norm, then for general operator measure, it's kind of complete mess. It requires some effort, and you have to be very careful about what you say. And for the matrix valued case, it's just like integrating. So what we have here, we take matrix valued function, we multiply it by vector valued function, take inner product with vector valued function, and get some scalar function as a result, and integrate with respect to scalar measure. So weighted norm in this case, in the case of matrix valued measures, is defined very easily, and The same, of course, you can easily generalize it to the operator valued norm if it has, if, for example, it takes values in trace class operators. So that is, and now kind of returning to the how matrix valued measures and related to perturbation theory. So again, we have the self-adjoint operator, and we can define matrix valued measures associated with some operator B, finite rank operator B, from D-dimensional subspace to H by the following formula that we just take this, where E is this abstract nonsense projection valued spectral measure from the spectral theorem. Now, in other words, we can say that M is unique matrix valued measure such that its Cauchy transform, which is just this integral, coincide with this resolvent, and we pre-multiply resolvent by B and post-multiply by B star. So that is just D by D valued function. So it's function whose values are D by D matrices, and here lambda is complex number. Let us assume that it is outside of R, or more precisely outside of spectrum. And now we can define the spectral measure for operator A gamma. And now I should say that when we first started kind of working with those objects, I kind of thought why people haven't looked at this before, and it turns out that of course they did, and they appear earlier, like in the 60s in works in early perturbation theory, in work of Kuroda and DeBranche, where they kind of use it, for example, use this language to prove Kato-Rosenblum theorem, and there were like different generalization. One when there is like trace class perturbation of a bounded operator, then there was like trace class perturbation when a resolvent, the difference of resolvent have trace class. So it's there was a lot of activities in the 60s, but I'm not going to discuss absolutely continuous spectrum. Now, what is kind of interesting in this? First of all, that why the spectral measure that I introduce is so important. And first, that operator A is unitary equivalent to the multiplication operator by the independent variables in this weighted space L2M. So, and it's kind of standard reasoning that unitary equivalence kind of can be found easy. So if we take vector E in the dimensional space and multiply it by C plus rational function, T minus Z is fixed. So here argument, the variable is T. And this vector in the vector space L2M will be going to operator to the vector in the Hilbert space H. And again, we can kind of integration, computing L2 norm, weighted L2 norm is not a big problem. And now I should, let me go back a little bit, that again, when operator B has rank 1, it is like usual scalar spectral measure associated with it is associated with vector B, and so that is just the standard fact in the kind of basic operator theory, and this basically proof is nothing new. Now, let me say something about a kind of statement of the spectral theorems the way I like it, because I kind of really don't like this statement with this operator valued measures, with this measure whose spectral measure whose values are orthogonal projections. It's kind of abstract nonsense. And I would like to have to work with von Neumann direct integral. And of course, it only works in separable Hilbert space, so my all Hilbert spaces are considered separable. So what is von Neumann integral? So what we do? We consider some abstract space, say D, Hilbert space, and some orthonormal bases there. And we have function n of variables. Xi, probably better to have x here, better to have x instead of xi, but okay, let's do xi. And so we have function measurable that takes values in integer. It's function n. It's so-called dimension function. And we consider space D of xi is just a span or closed linear span of first n basic vectors of the basis. And of course, it is subspace of weighted L2 space with values, with weight, with measure mu, and with values in E. And in fact, it's kind of well-known standard fact that if we consider all measures that are absolutely continuous with mu and n functions, those are spectral invariants. Of course, measure mu is not kind of unique. I can easily, by taking absolutely continuous function, I can the corresponding multiplication operator will be considered. The corresponding multiplication operator will be unitary equivalent. And what is this dimension function? If we compare it with representation in weighted L2 space with matrix weight, we can see that n of t is just rank of the W of t. So that is. And now, if we take Cauchy transform of our spectral measure mu, we can restore from this Cauchy transform properties of the measure mu. For example, if we take Cauchy transform of measure mu, then imaginary part up to a factor is just the Poisson extension of its measure. And kind of from a Poisson extension of a measure, of matrix valued measure, we can find out, for example, absolutely continuous part. It is just a non-tangential limit. Just non-tangential limit. And I can kind of make a small quick remark that very often if you take papers in spectral theory, they consider just like vertical limits along the imaginary axis, and we as analysts like to consider non-tangential limits. But for example, for bounded analytic function, it is the same. Non-tangential limit exists exactly at the same points where radial limits exist. And here Cauchy transform of measure is it's not bounded analytic function, but after linear fraction, but it has non-negative imaginary parts. So after linear fraction transformation, it will be bounded analytic function. So it really does not matter what limits we consider, vertical or just non-tangential limits. And what kind of important here that for rank 1 perturbation, the singular part of measure mu is carried by this set. So it lives on this set, where the limit imaginary part of this Cauchy transform is infinity. And kind of, I like this kind of piece of terminology that basically by support, I usually mean closed support, which is unique, and by carrier, I mean some Borel set outside of which measure is zero, and so carrier is not unique, but at least we know that measure lives somewhere in the set that I highlighted, and there is no measure outside. Now, why do we need this spectral measure associated with those vectors D? And so there is like standard linear fractional transformation relation between F gamma and F. And I remember what is F. F is just a Cauchy transform of the measure M, and of course F gamma is F gamma is Cauchy transform of spectral measure M gamma, and there is the standard okay, and just let me quickly move the slide up, kind of to show. I use this kind of standard resolvent identities. I use this standard resolvent identities to get this relation between Cauchy transforms of M and M gamma. It's kind of pretty easy. And we can rewrite those identities in this form. And in particular, it implies that the denominators of these formulas are invertible in upper half plane, and therefore the boundary values are invertible almost everywhere on almost everywhere on R. And now if we consider for imaginary part, we can see that imaginary part of F gamma is essentially the imaginary part of F and pre and post multiplied by some invertible almost everywhere matrices, matrix functions. So in particular, if you take boundary values, and boundary values are just densities of the corresponding spectral measures, they are just similar to, they're just one obtained from another by multiplication by invertible matrix functions, right and left multiplication. So the ranks coincide almost everywhere, so the dimension functions coincide almost everywhere. So it essentially gives you easy proof of Cator-Rosenblum theorem that absolutely continuous part of operator and its perturbation are unitarily equivalent. And in fact, that is what like Kuroda did. It's very pretty. And again, I'm not going to discuss absolutely continuous part, because whenever I discuss absolutely continuous part, everybody who did some kind of perturbation theory says, okay, and I proved something, I proved the statement like by a different method, or I use similar method in my paper, so I'm not going to discuss this. I'm going to discuss what happens with the singular spectrum. And there is classical Aronshine-Donahue theorem. Again, it's like late 50s, early 60s, that if you take for rank 1 perturbation, and we take singular parts of spectral measures of mu of the operator and of spectral measure of perturb operators, then the singular part are mutually singular. So in particular, if you think about matrices and you perturb matrix by cyclic vector, then your eigenvalues, all eigenvalues will shift. So you will never have equality of eigenvalues of original and perturbed matrix. And kind of general, it holds for all singular spectrum. And it's not as well known as Cato-Rosenblum's theorem, but kind of it is very easy to prove, because if you do simple algebraic calculation, we get this formula for the imaginary part of F gamma, and it's not hard to see that imaginary part F of gamma can be infinity if it can happen only if the denominator is 0. If the denominator is finite, then, and denominator is 0 is exactly when this limit is 0. And so the measure, the singular part of measure mu gamma is carried by the set. And those sets for different gamma are disjoint. So that is essentially the proof of classical Arenstein-Donahue theorem. Now, we say how to generalize it to the matrix case. And let me say one few things. That, of course, direct generalization is not possible. It's not true. And you can take like a simple example, like direct sum of two rank 1 perturbation, and just consider matrices, and you can take rank 1 perturbation of one matrix, rank 1 perturbation of the other matrix, such that they both have the kind of at least one eigenvalue in common, and so there are no mutual singularity. So one had to introduce some notion of directionality. So direction. So, and let me give the definition of vector mutually singular measures. So what is a vector mutually singular measures? So suppose we have two matrix valued measures, M and N. And we say that they are vector mutually singular if there exist measurable function whose values are orthogonal projections, such that if we pre and post multiply one, we get 0, and pre and post multiply the other, we get 0. Now that's completely agree with the classical definition. Okay, in my universe, I kind of in my language, identity and 0 are also orthogonal projection, kind of trivial cases. And therefore, in one-dimensional case, our function pi just take two values, 0 and 1, and that is just the classical definition of mutually singular measures. Now, what those identities mean? Okay, we know that measure M is W mu and N is W nu, where nu is trace. So it is just scalar measure multiplied by a function. Scalar measure multiplied by a function, and then we pre and post multiplied by functions pi. So we will get 0. And so essentially, this definition means that range of density W and range of V are orthogonal almost everywhere with respect to the sum of the mesh. And here I say that for appropriate choice of densities, because I can kind of go crazy, I can define density of W of mu kind of to be anything I want outside of the carrier, where the measure mu is 0. So I kind of have to be careful, so I don't have to go crazy. So that is vector mutual singular measures. And now I'm going to say that what we have this matrix valued singular part. And so, and the following theorem that if we have a two matrix valued spectral measure of operator and perturb operator, then, okay, I wanted to say that then they are mutually singular with respect to this vector definition, but you have to pre and post multiply one by another. One measure by gamma. And it really does not matter. Those two statements are equivalent. So you can pre and post multiply by gamma and gamma, or you can pre and post multiply by gamma the original spectral measure. And now, as a corollary, we get kind of the following result. So let us take a line in the space of D by D matrices. And let direction will be given by positive definite matrix gamma. So that is kind of essential. And take any singular measure. And then for all t, except maybe countably many, the singular measure mu and the scalar spectral measure mu of gamma s are mutually singular. And let me recall that the scalar spectral measure is just, I define it that mu s gamma is just trace of m gamma. So it is just sum of diagonal entries, so that is. And of course, it's everything kind of in the separable Hilbert space. And it's essentially kind of idea that it essentially uses separability of the space of the vector valued space L2 mu. Because if you have if you have that for uncountably many t, we have non-orthogonality, we have non-mutual singularity, we don't have mutual singularity, then we have uncountable family of vectors that are mutually orthogonal, which contradicts the fact that everything is separable. So that is kind of cool. Now, how we prove this theorem? One of the possible proof is based on the estimates of the singular integral and on the matrix Buckenhaupt condition. Okay, let me here abuse notation slightly, and if we have measure m, I denote by m of z, where z is of the real line, just the Poisson extension of this measure at this point. And we say that two matrix measures M and N satisfy joint matrix Poisson A2 condition if not sum. Okay, it's of course it's not sum, it should be supremum. If supremum, which is called, is bounded, if the supremum, which is conjoint A2 characteristic, is bounded. And I kind of, for those who know, it reminds very much the standard Mackenhaupt condition, but kind of essential for the matrices that you have to raise them to the power 1/2. And the definition is, of course, symmetric. And it's because of this power 1/2, it is monotone in the measure. So if we replace measures m and n by smaller, the adjoint A2 characteristic will be only smaller. Again, it's kind of 1/2 plays an important role. And again, kind of line ahead for those who knows that this matrix A2 condition is necessary for the Cauchy transform to be bounded between the matrix of two spaces. So where is Cauchy transform here? Okay, we define characteristic this operator T epsilon. So we define kind of rigorously what does it mean the Cauchy transform is bounded. So we introduce operators T epsilon. Of course, it is operator which is bounded in L2 W. Of course, norms can blow up when epsilon goes to 0. And operators T epsilon are uniformly bounded. If they are uniformly bounded, then the two weights satisfy this matrix A2, and that is kind of in all proved in all paper Treil Wolberg about wavelets in the angle between past and future. It was proved for case of one way, but so that is. But so how is this relevant for rank 1 perturbation? Again, it's a theorem due to Treil that if matrix M and M gamma be spectral measures, then all operators are uniformly bounded. Now, assuming this theorem and assuming everything, how we get immediately this corollary? Now, let me, so how we prove the corollary? Okay, if we have measure mu, multiply this measure mu by a function f by, say, integrable, then take it Poisson extension and divide it by Poisson extension of the measure mu and take a limit, non-tangential, then almost everywhere with respect to the measure mu, we restore function f. It's kind of classical result of harmonic analysis, and that's true for, of course, we get elementary from this matrix statement about matrix valued function. Now what we do, we take this product and we rewrite it in this way. Just take out the harmonic extension of singular part and take a limit. So we had this, and as we take limit, each fraction has a limit just corresponding densities. So this expression in the norm is just product of the corresponding densities multiplied by some kind of non-zero numbers. And this part goes to infinity when z come on the support of singular part. But on the other hand, we know that this product must remain bounded. So what happens? This goes to infinity. This kind of tends to the product of densities. So this tends to the W of x 1/2 W gamma of x 1/2. Okay, multiplied by some non-zero constant. And therefore, the only way for this product to remain non-zero, to remain bounded, is for this product to be zero. And that is kind of the proof of the corollary. And then that is how everything, that is how we get from the Mackenhaupt condition. Now, but how we get this theorem? How we get this uniform boundedness? How we get this uniform boundedness? And this uniform boundedness follows from the following theorem, which is kind of unitary equivalence. So, okay, we have operator A. Okay, and let us assume, we can assume this without loss of generality, that A is multiplication. Yeah, we assumed with loss of generality that A is multiplication by independent variable t in the L2 space with the measure mu, with the measure m. Now, the perturbed operator A gamma also acts in this space L2m, but it also unitary equivalent to the multiplication by independent variable in L2m gamma. So what operator gives us this unitary equivalence? And it is kind of not hard to show, to compute this operator that gives us unitary equivalence, this operator V gamma. And this operator looks exactly like a singular integral operator. And we can define operator T epsilon. So why the boundedness of this operator V gamma implies the boundedness of the operator T epsilon, uniform. And kind of the idea of the proof is very simple. Again, that is the theorem that I want to prove. That is the theorem I want to prove. And what is the main idea? So I apply this unitary operator V gamma to the vector HE. And then I apply the same operator. I shift my function in the Fourier domain, apply the operator V gamma, and then shift everything back. And if I do calculation, what I will get, I will not have in the numerator this kind of nasty thing h of t minus h of s. I will get just classical integral operator, just standard integral operator. And now if and it depends on the parameter a, and taking average over all a, and kind of doing some calculation, doing kind of standard calculation, I will get the desired conclusion. I will get exactly operator T epsilon. So that is. Now here is kind of interesting open problem that we kind of don't know how to solve. Something that we don't know how to solve. We have this formula for the operator V gamma, and if we act formally, what we can do, we can kind of take non-tangential limit as, for example, we can consider S in the upper half plane and take non-tangential limit as. And we can write, acting formally, we can rewrite representation as this, where plus minus means that we take non-tangential limit when we approach from above or from below, when we approach our limiting point. And of course, by classical results, everything exists in the sense for Cauchy almost everywhere. But what about singular part almost everywhere? And here is kind of the problem. But by the way, even the fact that boundary values exist almost everywhere with respect to Lebesgue measure, it just implies that this formula is true on the absolutely continuous part of the measure, and it can be used to compute the wave operator for the perturbation. And wave separators will be exactly multiplications by those two functions. Kind of gives the other proof. And for a general case, kind of for rank 1 case, existence of boundary values follows from Poltoratsky theorem, and it's not hard for nice function. But what is kind of interesting, what is kind of hard, what is interesting that Poltoratsky theorem is not known, existence of boundary value with respect to the singular part of the spectral measure is not known almost everywhere. And for high rank perturbation, it was shown by Kapustin and Poltoratsky that kind of straightforward generalization is not true. So this limit does not need to exist even. So, and the hope is that we kind of have to post multiply by appropriate projection, but again, we don't know, is there possible some generalization of Poltoratsky theorem? And so if we can make this formula be true, not only formally, but kind of really. And now in the last kind of couple minutes, let me say one thing about kind of exceptional sets. So again, remember I told you about this matrix Aronshine-Donahue theorem. Again, we have a kind of statement matrix Aronshine-Donahue theorem for finite rank perturbations that measures are orthogonal, singular part of the measures are orthogonal in this vector sense. So they have like orthogonal directions. But okay, if we consider the scalar measure, so if we take traces of those two measures, can we say something more. Can we say something more? And yes, we can. Kind of, we, for example, can say that this exceptional set has always Lebesgue measure 0. And that is kind of easy theorem that follows from the analog of Alexandrov disintegration theorem. And the integration theorem says the following, that if we average all those spectral measures m gamma along the lines, we will essentially get Lebesgue measure up to this operator gamma inverse. And that is kind of. And but remember, we had there is a drop. And remember, I had one of the corollaries, that if I take my parameter gamma along the line, so along the line gamma of t equal gamma naught plus t gamma 1, where gamma 1 is strictly positive definite. And if I fix some singular measure mu, then kind of exceptional set is just contains just countably many functions. Contains just countably many points at most. And kind of intuitively, you will have that this exceptional set then have to have drop in the dimension. So dimension should be like full dimension -1 at most. That's what our intuition says us, but intuition can be wrong because there are continuous functions whose graph has full Hausdorff measure. So graphs on a plane of continuous function whose dimension is 2, so that is. But in this case, in this particular case, the intuition did not fail us, and there is indeed a drop of the dimension. So dimension will be at least d squared -1, and that is the result with Wolberg and with Koniliau and Sasha Wolberg. And kind of one of the tools was to apply alt result of Mattila. And the main proof, the main component of our proof was to prove that some set is a Borel set. If somebody told me, like when I was studying mathematics, that I would need to prove that some set is Borel set, I would say, get out. But that is kind of, we just have to prove that some set is a Borel set. And that is just what we had. And of course, it is enough to prove that this set is analytic or Suslin set, but it didn't help a lot. So it was easy just to prove that the set is Borel. And again, and kind of set remarks that result can be generalized to the trace class perturbation. Of course, not as a result about the dimension, because infinite dimension, infinity -1 is still infinity, but the rest can be generalized to the trace class perturbation. And the result about absolutely continuous spectrum and kind of all this technique of matrix valued measures is not new. It's kind of names of Kuroda and de Branche are the main name. And the notion of matrix singularity is completely new, and the representation theorem is also kind of new, but it is generalization of the corresponding result for the rank 1 perturbation. Okay, thank you very much. And here are just some notes, and there is Arenstein paper, there is Donahue paper, there are papers by Kuroda, and there is paper for de Branche, and kind of a lot of, and the paper by Matula. Okay, thank you very much for the attention.
Thank you. Thank you.
Okay, any questions?
Are there any questions from the audience?
Sergei, can you come to the slide? Can you come to the slide where you said that you cannot divide by Poltoratsky matrix stuff?
Yeah, this one.
Maybe previous one.
No.
Again, another previous, more. Why not to divide just by Cauchy transform of scalar measure mu, which all of them are absolutely continuous with respect to this scalar measure, which you get as trace? Why not to divide by it?
So because it's not straightforward. So what we need here, what we need here. So what we need here. So what we can do, for example, we can consider instead of S, we consider S plus I epsilon, and then let epsilon go to 0.
Mm-hmm.
We split this integral into 2,
Mm-hmm.
and we have to have limit. And what we will need something that a limit as epsilon goes to 0, say from the right, get gamma integral h of t minus s plus I epsilon. And now we get dm of t multiplied by vector e.
Uh-huh.
And we need to have this with m gamma singular almost everywhere.
Right, but if you just divide by Cauchy transform of mu s gamma, not mu s, right?
Yes, mu s gamma. So that is.
I see. Mm-hmm.
So in fact, what is kind of.
Mm-hmm. So boundedness exists, but convergence is not clear.
Yeah. So the boundedness exists. So we can take with this f plus minus, with this f plus minus and c plus minus of mf, we can take like weak limit points.
Mm-hmm.
So we don't know, for example, that weak limit exists, but we can prove that weak limit points do exist.
Mm-hmm, mm-hmm, mm-hmm.
And so here, okay, I can make sense of this formula where I say that f plus minus and this c plus minus are some weak limit points corresponding, for example, to the same sequence.
So you changed the notion of convergence instead of
yeah.
Uh-huh.
Yeah, so it's just not weak and.
Yeah, the same problem exists in this non-homogeneous harmonic analysis, right?
Yeah, yes, it's always kind of it's always the problem with this. So it's, and to get kind of through everything, you probably need to go through like Clark model and everything, but still it's
Okay, I see.
it's not easy. So I cannot prove existence of like weak limits, not weak limits. And again, the problem for the absolutely continuous part,
Doesn't exist.
everything works, and even strong limit exists, and this multiplication operator, those multiplications operator are wave operators. So that is everything you need to do. So the problem is with the singular part.
Yeah. Thank you. Thank you.
Any other questions? Okay, well then let me thank our speaker very much again and the audience for participating, and hopefully next week. Bye.
Bye, everybody.
Thank you, Sergey, again. Thank you. Bye.
Bye.